and welcome to the 6th lecture in the basics of hemodynamics. With this lecture here, we'll utilize previously learned hemodynamic calculations to assess stenotic valve lesions. We'll apply the calculations themselves in practical form, and we'll learn the normal reference ranges for determining severity. We'll review the limitations and assumptions associated with these methods for valvular evaluation, and we'll introduce a new principle of the pressure half-time. These may also be used to evaluate stenotic lesions, not just regurgitant ones. Again, the principle of hemisphere applies, knowing that the volume of blood within this dome will also pass through a narrow orifice. So we have our equation: effective orifice area is 2 pi r squared times the velocity associated with aliasing and the velocity of blood moving through the stenotic lesion. This is all fine except for when accessing atrioventricular valves, particularly the rheumatic valve with rheumatic stenosis. In this pathology, the valve leaflets billow in direction of the flow, a bit like sails in the wind, so there is an effective funnel shape during the flow. To measure the radius from the leaflet orifice and place a dome over the top makes an assumption of a formed hemisphere incorrect. The actual area within this would be less. And so to do this, we include alpha, which is the angle divided by 180 to correct for it. And we can see that in this instance here. So we don't have a perfectly flat area, we've got a funnel shape here. So we measure the first alias for our radius, and then we also measure the angle. There are early diastolic filling and atrial contraction forward flow profiles through the mitral valve. It is the early diastolic velocity that must be measured. Here we have an example. Say we measured a radius of 14.2 millimeters, and the aliasing velocity occurred at 0.45 meters per second. The maximum velocity through the valve in early diastolic filling is 1.8 meters per second. And we measured the angle. Some systems can actually do this themselves. Other times you've actually got to apply a protractor to the screen and work the angle out. And in this instance, it came out at 135 degrees. Popping all the items into the formula and correcting for meters going into centimeters per second and millimeters going into centimeters, we then come out with 3.17 times 0.75. So our effective orifice area is 2.4 centimeters squared. The applicable PISA considerations that were for regurgitation also apply here for stenosis. In addition to this, we must understand that the orifice, particularly for mitral stenosis, is elliptical in shape and not circular. Thus, a hemisphere will only approximate the volume of blood within the dome, which we can't actually correct for. Now that angle is introduced, there is a potential for incorrect measurement, and as mentioned, that some ultrasound systems do not have this capability as part of their measurement package. A protractor is placed on screen and manual alignment may be required. We must also consider that the mitral valve is saddle-shaped, thus measuring in one view may not be an overall representation of the angle as formed in stenosis. The continuity principle is our grounding rule we use in our evaluation. What goes in must come out between two areas of the heart in a closed circuit. Therefore, flow in the left ventricular outflow tract must equal flow through the aortic valve in the absence of a membranous ventricular septal defect. As we can see here, stroke volume through the LVOT is going to be equal to stroke volume through the aortic valve. Consider if there was a perimembranous ventricular septal defect. A cross-sectional area of the aortic valve calculation would be distorted. Stroke volume through the LVOT would be greater than what goes through the aortic valve, as some of the blood would actually move through the shunt. The aortic valve area would be larger than expected, leading to an underestimation of the stenosis severity. Mathematically, the principle is demonstrated here. We know stroke volume is equal to the cross-section area times velocity time integral. We know that the cross-section area can be further broken down to 0.78 times the diameter squared. So we say what goes in must go out. The stroke volume through the left ventricular outflow tract must equal the stroke volume through the aortic valve. And expanding both sides, we get this. When we're working with our formulas, we want to work out the cross-sectional area of the aortic valve. So we rearrange our calculation. So it works out to be the cross-sectional area of the LVOT times the velocity time integral of the LVOT divided by the velocity time integral of the aortic valve. The diameter half is the radius of the left ventricular outflow tract. To minimize the effect of the assumption that the left ventricular outflow tract is uniform in size, it is important when evaluating the aortic valve that this measurement is made in mid-systole during flow. The VTI is obtained by placing pulse wave Doppler in the left ventricular outflow tract at the valve level and moving the sample volume backward towards the apex to minimize flow acceleration and remove valve clicks, or basically leaflet motion. Using the machine measurement tool, we draw around the flow, thus capturing the entire range of velocities over a period of time. The velocity time integral of the aortic valve is obtained by placing continuous waves through the valve and obtaining alignment most parallel with the flow. This means investigation from multiple windows, such as the apical, suprasternal, supraclavicular, and right parasternal windows. However, the location for the probe placement is not limited to these. A subcostal or left parasternal window may offer the best alignment. Finally, a good sonographer will always use the continuous wave probe for the investigation. It is considered bad form to use the standard imaging probe alone, as the CW probe will obtain the same velocity, if not higher, due to its design and purpose. In this example here, we can see something that's been obtained from an apical window where we've got a downward directed flow. And on the one on the right here, we can actually see a forward directed flow, as we'd expect to see from a right parasternal window. Putting the continuity equation into practice, we take down the measurements. So we have our left ventricular outflow diameter at 20 millimeters, the velocity time integral of 12.3 centimeters, and an aortic velocity time integral of 26.5. Have a go at working it out yourself. Press pause now and resume once you're done. So putting it all through here, we can see cross-sectional area of the aortic valve is 0.785 times 1 squared times 12.3 divided by 26.5, which gives our aortic valve area of 1.1 centimeter squared. So we can use our valve areas from these calculations to work out severity according to the scale here: mild, moderate, severe. And in the instance of aortic valve, between 1.5 to 2 is only mild, and if you actually had a valve area of under 1 centimeter squared, it actually indicates it's severe. So expected findings that we see with valvular stenosis. Consider aortic stenosis. There is increased effort to push a forward stroke volume through the valve. The maximum velocity will be increased and the flow duration may decrease. In response to the increased effort, the left ventricle will hypertrophy. Associated with this is the secondary finding of diastolic dysfunction. Through progression of many disease states with increasing severity, we will see abnormal relaxation of the left ventricle, then move to reduced myocardial compliance, and then markedly reduced compliance. A common 2D finding that we'll find with aortic stenosis is aortic root and ascending aortic dilatation. The stroke volume calculations using the principle of conservation of mass are based on a simple hydraulic formula that assumes that uniform flow is moving through a fixed cylindrical tube. As previously noted, there are instances where these do not always hold true. The diameter may not be measured correctly due to suboptimal imaging. This may be due to significant calcification, annular rings, valve repairs, or replacements. The incorrect determination of this value impacts the end result significantly. The incorrect timing of the cardiac cycle may also be used. One of the above assumptions is the cross-sectional area is fixed. However, this may change throughout the cardiac cycle, insisting on diastole. The correct timing is mid-systole for the semilunar valves and early diastole for the atrioventricular valves. It is important to note that a velocity time integral may not be accurate. The modal velocity and leading edge need to be applied and traced appropriately. Parallel alignment to the flow is required, and the ultrasound beam being off angle will reduce the end result of pain. The placement of a pulse wave sample volume, particularly for the left ventricular outflow tract, needs to be in the correct position. The sample volume too close to the valve will collect flow acceleration and may be associated with opening valve clicks. Beat-to-beat variability needs to be minimized with averaging and appropriate tracing chosen. The stroke volumes through two locations may not be equal when there are intracardiac shunts. When there is perimembranous VSD, the stroke volume through the left ventricular outflow tract will be greater than that of the aortic valve. This would lead to an overestimation of the aortic valve area. Similarly, when we're assessing the mitral valve area and the left ventricular stroke volume is calculated in the presence of aortic regurgitation, the stroke volumes are not equal. Flow through the aortic valve is greater than what is through the mitral valve, and thus we obtain a similar result. However, if there was mitral regurgitation and the aortic valve is competent, the opposite is in effect. Stroke volume through the mitral valve is greater than that of the left ventricular outflow tract, and underestimation of the valve area occurs. If the simplified equation is used with the substitution of a velocity time integral with peak velocities, the user must be aware that the flows through the LVOT and aortic valve are not simultaneous, and therefore may not accurately demonstrate the maximum velocity at one point in time. An additional problem may be encountered when using peak velocity for prosthetic valves, as there is rapid pressure recovery of flow moving through the valve and localized higher velocities. That this method they may underestimate the actual valve area. Finally, we must consider that when there is poor cardiac output, that the flow may not sufficiently open the valve. In these instances, the valve may overestimate the severity. Determination of whether aortic valve is significant in stenosis and warrants patient management is challenging when there is also severe LV systolic dysfunction. A patient may require a dobutamine infusion at low doses to stimulate an ionotropic response and increase contractility. When the patient does not have significant stenosis, the sonographer will observe a larger increase in the left ventricular outflow tract velocity over the aortic valve. A recalculation of the valve area will show an increase. In the presence of severe aortic stenosis, the VTO for both will increase proportionally and thus not affect the calculation of valve area significantly. Now we can investigate the pressure half-time use for mitral stenosis. The use of a deceleration slope for mitral inflow wave profiles may be utilized to determine the deceleration time and from that, pressure half-time estimations for the mitral valve area. The methods are widely used for the simplicity of use and the fact that the measurement is not influenced by cardiac output states or in the presence of mitral regurgitation that influence the continuity equation. So what is actually being investigated? The time taken for the pressure to decrease in half from its original value. With the systems, we measure the velocity, not pressure, so the principle is as follows. Pressure to equal half the peak pressure, working pressure into velocities, 4v squared, and half 4v squared of the peak. We can then substitute numbers across. The 4's basically cancel out. Then we get the velocity squared is equal to the velocity squared peak divided by 2. Then we can actually remove the squaring and the square roots, and we come down to the velocity that we want to have for a pressure half time is the peak divided by square root of 2. Or another way to represent it is velocity peak divided by 1.414, or the velocity peak times 0.007. Fortunately, the ultrasound system works this all out for us. All we simply need to do is measure the deceleration slope. The relationship is that the pressure decreases in half is 29% along the slope. Thus, pressure half time is equal to deceleration time times 29 divided by 100. Or pressure half time is deceleration time times 0.29. The mitral valve area then can be calculated by the use of the constant 320. Mitral valve area is 220 divided by the pressure half time. Then by combining both the formulas here, we have mitral valve area is equal to 220 divided by dt times 0.29 from up here, or equivalently 759 divided by deceleration time. Of course, there are considerations and limitations that also apply with this principle. Sometimes a mitral flow inflow profile can be difficult to obtain a true trace for the early diastolic filling, and thus the resulting deceleration slope. In some instances, the deceleration slope may look like a ski slope. So where does the sonographer actually make their assessment? So where possible, the user must use the mid portion of a deceleration slope. So if we have our deceleration slope looking like this, we want to take the mid portion and measure our deceleration slope as measured so. Diastolic dysfunction is a topic we will cover shortly. This disease process in its later stages can actually lead to heart failure in the presence of good systolic function. These are a result of prolonged relaxation and/or reduced ventricular compliance. In prolonged relaxation, as we can predict, the deceleration slope will be increased, falsely indicating a greater severity of stenosis. Conversely, when reduced ventricular compliance is observed, the flow into the ventricle is short, and thus a short deceleration slope is obtained. Significant aortic regurgitation will influence the mitral inflow profile. Aortic regurgitation occurs in diastole, so both flows contribute to the filling of the volume of the left ventricle. This shortens the duration of flow from the left atrium, and as with reduced compliance, the deceleration slope is shorter than expected, leading to an overestimation of the valve area. In the presence of an atrial septal defect, blood may move through in the direction of the shunt into the right atrium or through the stenotic mitral valve. As flow will take the path of least resistance, significant blood flow may move through the shunt and thus reduce maximum velocities of the mitral flow profile, and thus the deceleration slope that is measured. Also, immediately after mitral valve balloon, valvuloplasty, or cardioversion, left atrial compliance and function will be affected. It is not appropriate to perform the pressure half-time calculation in these instances. In summary, the PISA also has its place in measuring stenotic valve lesions. The most commonly used method for calculating the valve lesion is the continuity equation. Both PISA and continuity method have assumptions, and it is important to note that limitations may significantly affect a valve area calculation and what we must do to minimize these. And the pressure half-time is a simple method to work out valve areas that correlates well with other quantitative analysis forms.